Next section is chapter 24, section 5, and it is the potential due to a continuous charge distribution. Now we've seen the point charge and also the dipole and the potential due to those charges. Now this is the first time we are kind of entering the distribution of charges. And for this part, the lesson objective is that for charge that is distributed uniformly along a line or over a surface, we'll find the net potential at a given point. That means we will do very similar calculations to what we did in chapter 22 when we calculated the electric field using integrals, and that's 7-step process. So again, in this chapter, I'm going to show you how to do the steps for when you calculate the potential, not the electric field, but the potential. First of all, just like the electric field, we couldn't use the point charge electric field, right? And then if there was a charge distribution, and now we need to use it as a small charge like dq, infinitesimally small charge dq, and then that contributes to electric field as dE. So it's a very small electric field contribution as well. So we have the same thing here. We are modifying the point charge equation for V, which is 1 over 4 pi epsilon naught Q over R. So we are really saying that, okay, let's take a very small charge and that is going to create a very small potential. Okay, so that's how we start. And dq can be positive or negative. In this case, in the electric field, we did not take the negative one because we figured out the direction first, but there's no direction in potential calculations. So we need to think about whether this is negative or positive q. And so the right side, so when we do the integral, the left side is going to be simply v, right? And the right side, this 1 over 4 pi epsilon naught is going to come out because it is simply a constant. So you have only dq over r in the integral. So you can integrate this over charge. So it's very similar calculation to what we did in the electric field. So here's our first example, a line charge. So this charge rod is not a particle, right? It's not a point particle, so it's a rod. So the charge is distributed over a line or linear charge distribution. So I'm just gonna check this one first and we will go back and take some notes. And then, so part B here, we can treat this element as a particle. So what we are doing is, as you can see here, we are taking a piece and we are calling that, so this is our dq here. And that dq has a length of dx because it's on the x-axis. Okay, and then once again, just like we did in the electric field, you don't take it from the beginning, from the end, so not from the ends or not from the middle. You want to choose an arbitrary point so that you can find the general geometry, and then so that you can use it for any point. Okay, so next step is again defining from that distance to the point of measurement. So this was dq here, right here, and then that charge is at a distance of r, and you're measuring the potential at point P, right? So instead of q, you have a dq basically, and then next step is to add the potentials due to all the elements. We need to scan through this rod, and you start from the leftmost element. So that means that this kind of tells you the intervals, and this means your r is simply d. That was what the value is when you are at the leftmost dq. So this is still dq as well. Okay, and then you're gonna scan it through, and then if you go to all the way to the right side, and your r becomes this r. Okay, it used to be d, now it's r, and you can find it as, for example, here in root d squared plus l squared, right? Because x goes to l, from here to there is l, and from here to there is d. So and it's perpendicular to each other, so that you can use Pythagorean theorem to find that hypotenuse, and that is d square plus l square in the root. So those are the intervals. And what you need to do next is, since you had this equation here, you just need to put those back in there. First thing is dq, right? And you're gonna put it in terms of dq, replace it with dq, and r becomes the value. So again, if you think about the intervals, if you look at figure D and E, D looks like r is equal to D, and E, r equals to d squared plus l squared in the root. But the r value we need is none of those, because those are specific values. So we want it for here, for part C. Okay, so when you look at that, so I'm going to write these down on the previous page, but when you look at this r is equal to, so this part is x and this part is again d. They are perpendicular to each other, so you can do x squared plus d squared, take the root. That gives you what r is. Okay, so that's why we have x squared plus d squared in the root as a replacement to r, and dq is replaced with that. And then we will take the integral. So let's go back and do this. I just wanted to explain that, how we take that dq, just remind you what we did, and because we did something similar in the electric field. Okay, so let's get started. First thing, step 1, we are writing dq in terms of charge density. Since this is linear charge, we are going to use the charge density, linear charge density lambda, and it's not q is equal to lambda L, it is dq, so I need to write the L in terms of differential as well, so I'm going to use dx instead, because L, as you can see on the figure, is on the x direction. So what is step 2? Step 2 is modifying the point charge potential. It was k q over r, q goes to dq, and dq is going to create a potential which is dv. Okay, not just v but dv. Step 3 is using some geometry. Again, let's take some arbitrary distance here, and then we will say that this is r, this is x, r becomes x squared plus this is square. Let me fix that. This is x squared plus d squared. That's what r is. So we're gonna, for example, need r in the equation, as you can see, and we are gonna replace r with x squared plus d squared. Let's take note of that. And that's from the geometry. And we don't need any angles, because again, potential is not a vector. We don't need to figure out any of those components, because there's no such thing. And then step 4, so they're little shorter steps because it's not a vector. We're gonna put these together. So we are putting this definition of dq here and this r value here, and let's do that. dv is k lambda dx over x squared plus d squared and 1/2 to the power. So we combine them all in step 4. Okay, and step 5 is going to be simply integrate. When you integrate, you're going to take the integral of both sides, right? Left side is going to give you v. Right side, you have k, you can take it out. Lambda can be taken out, so these two are constants. Take them out, k lambda. And the integral is x squared plus d squared to the 1/2, but negative 1/2 dx, right? That's what you have left with. And the intervals are, since you're scanning from this point all the way to that point, you're doing that along the x, right? That's what you're integrating over. You need to think about x values. X starts from 0, goes all the way to L. And this integral here is not an easy integral to solve. There you use some trigonometric functions, some identities, and I'm not going to ask you how to solve this, so I will also just put the value, like the answer in. So that integral will result in an natural log ln function, and the inside I'm just gonna copy what I have, x plus x squared plus d squared 1/2 divided by d. Okay, so that's what the answer of that integral here. So this integral here is exactly what this is here. Okay, and you can see that k lambda is in the front. And what you need to do next is to submit those intervals, and we are going to get the answer to this after that. So we have k lambda. After putting the integrals in, we end up with L plus L squared plus D squared 1/2 divided by D. The zero term goes away. And forgot the ln. We have natural log right here. Let's make more space there. This is k lambda ln of this function, natural log of that, so we still need to have that, and that is the potential. And there was -1, but ln1 is simply 0. Okay, so when you put that 0 in it, you're gonna get 1, and 1 is simply ln1 is 0. So that's why I not putting it in here. So yeah, that's the function of the potential at point P when you have a linear charge distribution, as we had it here. And this is again the answer.